the talk is going to be divided into two parts. I will give a presentation that is going to last about 40 minutes. And then I'll do a short demo of how to install packages and how to run an example Julia script on Biowulf. So I have already requested, I have already started my connection to Biowulf using SSH, and I've requested a few resources just so that they're ready. I will let you know when we get to that point, so that you can start requesting your resources on Biowulf. Again, you can follow the example as I do it, and if it's up to you if you want to do it at the same time, you can work on the exercise later as well. As Wolfgang said in the chat, there is the talk, the slides for the talk today are already in PDF format, and they are in our webpage. He has put the link in the chat box, but here is the link: hpc.nih.gov/training/handouts/julia4sc.pdf. Or you can also go to a training page in our webpage, and it should be up on top. So the first time I heard about Julia was back in 2013, and this was I was doing research at another institute in the campus, in the NIH campus, and my my supervisor suggested that I use Julia for a research project I was about to start. At the time, it was he had heard from a personal source that Julia was a language that you can use to script very easily, and also that it was fast compiling. The project consisted of brain simulations, and those needed to be done in parallel, and we needed to do many of them. So the idea was that Julia was the perfect language to do that. Unfortunately, at the time, back in 2013, there wasn't enough information about Julia on the web, and not a lot of support, and not a lot of not that many packages. Python was the thing to do, so I ended up using Python. But I always wondered what would have been like if I had used Julia for that research project. So I will show you later how things have changed. The picture has changed for Julia, and it's looking pretty good for Julia usage. But let's go directly to the outline of the talk today. So I will give you two goals that I have thought of for the talk, followed by the motivation. What made me wanna and others wanna give this class today. And it's important to get a brief historical perspective on Julia, especially because Julia is such a young language. I will also compare Julia with other scientific computational languages. Many of you have already used one of those languages. Specifically, I will talk about Matlab, Python, and R as compared to Julia. And because we would like to do scientific computation with Julia, I will give you just a brief list of the packages that you can use with your scientific computation projects in Julia. Also important, the IDEs, or integrated development environments. These are the editors that are most developed with Julia. I will give you a short list of what they are and how you can use one of them on Biowulf. And then I'll follow with an example. This will be a machine learning example. Since the early days of Julia, the thinking was that it will be good to have a computer language that was explicitly made to optimize machine learning, and this was Julia. I will use a package called Flux. Flux is a machine learning package, and it's one of the better developed packages in Julia. And then we'll close with a conclusion. So let's start with the goals. At the end of this class, I am hoping that you should, well, number one, have a general idea of the pros and cons of using Julia on Biowulf and beyond Biowulf for scientific computing. And number two, I I hope that you have also a general idea of how to run Julia scripts interactively on Biowolf. For the scripts, also I will show you how to install the packages needed for the scripts for this example script to run. So you would also see how to install packages in the Julia interactive shell. And just to mention that I am not going to cover how to submit Julia jobs on batch mode on Biowolf. We will only do it interactively. So the submission of batch jobs is a very interesting issue in of itself, but we can cover that in future classes. So the motivation, the reason why we're giving this class is because first, there's always a need for a language that can run fast but have a high level syntax. And by high level syntax, I just mean an easy to code commands into, such as Matlab, Python, and R. But we want to get our code to run fast as it scales up. As you create many jobs in parallel and want those to run or need those to run fast, then this is always something that is very desirable. You have something that you can run faster than the current languages, and we'll see why that this is a controversial subject. It is, of course, desirable also to be familiar with Julia, given that Julia, the usage of Julia is growing in science and in general. I will show you a few graphs later with the trends of the Julia growth, which has grown tremendously in the past 2 years. And of course, there's a need for a language that can make use of other languages packages. As I will mention later, Julia still has a relatively small number of well-developed packages. So many people have use other languages packages. Just to mention a few, you can make calls to Python, R, Fortran, C, and others. And even if you were not going to use Julia for a project, or if you're not going to be using mostly Julia, it is always useful to be familiar with other scientific computation languages, especially if we think that they're going to become important in the future, as I do think it will be. So the history of Julia. Julia only started in 2009, so it was fairly recently compared to the others. This was the idea of 4 collaborators who had, as I mentioned before, wanted to create a language that had a high level syntax and at the same time fast performance. Like they say, they wanted something that was as easy to code like Python and ran as fast as C. It was only in 2012 that Julia was released to developers to contribute to the code. So it's very, very young, like I said before. But this is a good sign. In 2014, the Julia Academic Conference started, and this is a good sign for a language when a conference solely dedicated to that language starts happening. In this case, the 2019 conference had about 400 attendees, and then the 2020 conference happened only virtually and had about 10,000 people that registered and 24,000 people that watched the YouTube presentation, the keynote. So it did have a big impact in the past year. Just to show how young Julia is, the 1.0 version was only released in 2018. So that was about 3 years ago, 4 years ago, almost. And this is something important for those of you that use VS Code. VS Code is a very powerful editor that you can run locally on your desktop computer to edit, debug, version, and run code remotely. So the extension for Julia is very recent, and 1.0 was released in 2020. So if you are interested or have used VS Code before, for you to know that there's an extension out there for Julia. And more recently, Julia 1.5 was released. It's just another time point. So, but I also wanted to give you the picture, a picture in numbers of how Julia looks like within the Biowulf community. And I believe this might even reflect what is going on in the in the rest of the NIH community in the campus. So this data that I'm showing you here is from the past year, the year that ended on 16 March 2021. It's only for the last year. And so we have, if we look at number of unique users that have used Julia compared to Matlab, Python, and R, we see that there's a huge difference between Julia and the others in number of unique users, whereas R has almost 1,000, had almost 1,000 users, and Python had 764, Matlab a smaller portion, Julia had a very small portion of those users. So within the Biowulf community, and you should know that it's still the number of users that have used Julia in the past year is not as large as those users that have used the other big ones. So now the number of module loads for Julia compared to MATLAB, Python, and R on the right-hand side of your screen. So this is for those of you who are not familiar with how applications are organized on Biowulf, applications are organized as modules. And so this means that when you want to run an application, you have to load a module for that specific application, in this case for that language. When you load a module, a set of whatever is necessary to run that language or application is set up, such as the library paths, things that need to be added to your path are added to it. And if the application uses Singularity containers, then Singularity is loaded, and so on. So by looking at the number of module loads, this gives us a proxy of how much a language is used. So as you can see on your screen, R has the huge amount of 13.8 million module loads just in the past year. So that really dwarfs all the others. Python had 1.3 million, and MATLAB and Julia had a very small share of that, with those module loads. And we also we have to consider that R is needed for a ton of biomedical applications on Biowulf, and this is why they need R. If they need R, then the R module is loaded many more times than the Python module is loaded. So just a reality check for you to know what Julia looks like on Biowulf at the moment. But on the brighter side, we have this is a graph that I reproduced from the PYPL index. It's a commonly used language of popularity of language index, and they use the frequency of tutorial searches on Google as a proxy for the popularity of a language. And so we can see that Python has a huge share of the popularity according to this index with a 30%, and basically is a lot larger than any of the others. And we can see R with 3.8% and MATLAB with 1.8%. This is in the past year. This is in the year that ended in March 2021, so very recent. But we can also see Julia in place number 26 with 0.35%, even though 0.35% popularity doesn't seem like that big. It is a big deal to rank 26 among the most popular computer languages worldwide, according to this index. And if we also look at the growth of that popularity using the same index, we can see how the popularity of those languages has evolved over time. In this case, since 2005. So we see Julia, Matlab, and Python growing steadily, and then either staying stable at around 2017 mark, or going down a little bit. But we see Julia going up down there, especially since 2020, mid 2018. It's been going up more consistently. And so the next slide, this slide is showing, this is from the newsletter from January 2021 from juliacomputing.com. This is really showing the tremendous amount of Julia growth in usage of Julia in the past year. So we have in the red box, we're showing the number of Julia downloads. This is in the past year from January 1st, 2020 to January 1st, 2021. And so it's almost doubled in the number of downloads. The number of Julia packages has increased significantly as well. But as I will show you later, the number of packages doesn't really mean that those packages are well developed. So we will talk about that a little bit later. But it's still it's a big surge in the number of packages available, publicly available to use with Julia. Another thing that we can look at is the YouTube views of the Julia language channel, and that also has increased over 100%. The number of citations for the Julia papers has also increased 50%. It's just a very good sign of that things are picking up for Julia. This is another index. The one you see on your screen is the TOB index rank. It's just a different way of ranking computer languages worldwide. This uses the number of skilled engineers in a given language and other different factors to rank languages. And we see that Julia has gone from place 47 to number 23. So a change of 24 in the ranking. That's pretty big. So it's looking good in the past year. So if you are considering using Julia, even if it's not as your main language, this is something to think about. So, but I also wanted to give you a view of what it looks like, what things look like, what things are like in Julia versus Matlab, specifically Matlab, Python, and R. So Julia, as I mentioned before, it's a very young language. The first release was only in 2009. Compare that to the others, especially Matlab, that's been around since the 1980s. So if a language is young, you have to think that the development of the language, is going to still change significantly before it stabilizes, and like it's happened for Python and Matlab and R. The number of packages, this is a little bit of a relative number, but we can see Python has a huge number of packages available publicly. And so this is 290,000. I mean, that's a huge number. You basically, for anything you want to do on Python, there's a package for it. And most of those packages are good, are very well developed. You have less so in R, but that depends which repository you're talking about. So it's relative. Of course, in Matlab, things are a little bit different because you have the Matlab toolboxes themselves, which you can obtain from the MathWorks website. And you also have the third-party toolboxes. So as far as I know, there's not a unified listing of third-party toolboxes available for Matlab. So, but that's probably the number I'm showing you there is probably an underestimate of what the real number is. So Julia has at the moment, or had a month ago, 4,800 packages. And of course, most of those packages are have been recently developed. And so there's only a small subset, relatively speaking, that have been around for since the origins of Julia, and that are very stable and well developed. So we'll get to that in a minute. The current version just shows you the length. It's just a proxy for the length of a language, the length a language has been around. And the package repositories for when you install packages in Julia, it really has a similar feel to that of R. R is very lightweight, so is Julia, and you install packages only if you need them and as you need them when you need them. And Julia comes with an integrated package manager, and it's very nice. It's you can run it interactively or as a function, and it allows you to install packages from an online registry. So all you need to download and install Julia packages is to an internet connection. So that is a great thing about Julia, as it is for Python and R. So for IDEs, just like Python and R, Julia has a few IDEs. I will mention a couple of those a little bit later as the ones that we have experience with on running on Biowulf. So next item is the computational process. And this, I realize this is not, there's not a clear cut between compiled and interpreted languages, especially since what is compiled or interpreted is not really the language, but the implementation of a language. So a language could have compiled implementations as well as interpreted implementations. I will go into detail on what the difference is between compiled and interpreted, and as well as how Julia does the compilation. But suffice it to say, for now, Julia is supposed to be a compiled language, and so it's supposed to be faster when you run it, faster than the implementation of those other languages shown in the screen that are not compiled in principle. But as I said before, there's not a clear-cut line, and things get a little complicated. But we'll talk about it later. The structure of the code, the structure of the code in Julia is very similar to that of Python and R and Matlab. Perhaps the only difference is that Python uses an indented structure, and this means, for those of you who have coded in Python and have gotten used to it, you stop thinking about that after a while, but Python requires the code to be, your scripts to be indented in a specific way. Julia is freestyle. I'll show a few examples in a little bit. So the typing, Julia is dynamically typed, just like the other three shown on the screen, Matlab, Python, and R. This just means you don't have to declare the type of functions before you use them in simple terms. And if you are planning on using machine learning or deep learning in Julia, know that they are well-developed packages to do that. And just to mention two, we have Flux and KNet in Julia, although people do use Python calls to the Python packages for machine learning as well. So another slide. This slide is showing the notebooks in the first row. So if you are familiar with Python with Jupyter Notebooks or Jupyter Lab, this is a way to run your scripts interactively on a browser. And you should know that you can actually also use Julia as your kernel for Jupyter, just like you do with Python and R. And in fact, the first two letters of Jupyter, they come from the name of the language, Julia. For visualization, Julia has its own, has a standard library, the plus.jl. You can also since you can interface with Python using Julia, you can also decide to, if you're not satisfied with that package, you can use the Python packages in Julia. And for package installation, Julia, as I mentioned, Julia has a built-in package manager. It does really feel a lot like being in R. You install packages when you need them, and you can do it interactively in the Julia shell. And I'll show you in an example how to do this. To load packages, again with Julia, you install packages. Then if you're going to use them in a function or in a script, you have to import them, and just like you do in Python and R. In Matlab, there's no need to import. You just need to use a function to be able to use a specific toolbox. And the two items on the bottom, array indexing and assignment, I just mean to show how similar Julia feels even the first time you look at a Julia script. And there's more examples here. So the first time I saw a Julia script, you really, if you have coded in MATLAB, Python, and R, or in all of them, you really feel like you're familiar with the language already. It's so similar. There are exceptions, but it's so similar that you can understand somebody else's scripts easily. And so this is important. But I mentioned earlier I was going to go into the differences between interpreted languages or implementations of a language and compilers, and there's a third way, the way Julia does it. And Julia is not the only one to do it, but Julia uses something called just-in-time compilation. So an interpreted language shown on top of the slide basically just means that you start with your script and you run that by an interpreter. An interpreter in simplistic terms, it just looks at the first line of the code and it translates it into machine code, sometimes not directly, sometimes there's an intermediate code, it just depends. But let's just assume for the purposes of this cartoon that you turn it into machine code and then you run it. And then you go back, after running that line, you go back to the interpreter and you go to the following line. So this is how, in simplistic terms, an interpreter works. So the advantage of this model is that you don't need to wait very long for your script to start running. It runs almost immediately. Excuse me. So the disadvantage is that he has to do it line by line. So when you're running one line, you have no visibility over what happened before that line or what is going to happen after. So if there are any optimizations to happen in the script itself that need knowledge of the script as a whole, then it cannot be done. So when you start doing things that are more and more, as the things you do become more and more complex, this can really mean a very slow language execution. And then on the other hand, you have compiled languages. And by compiled here, I mean ahead of time compiling, which basically means you have your script and then you run it through an ahead of time compiler that turns it into machine code, and then it's saved on disk. And then you can use that same compiled, that has been saved, same compiled machine language script. You can run it as many times as you want. The machine code has been generated to be specific to that machine or that CPU in which is running, in which has been compiled. So it's very fast. And if you want to run many copies of the machine code, then if you need to run many copies in parallel, then that is super fast. The disadvantage of this compiled model is that if you need to change something in the code, even if it's something small in your original script, you're going to have to go through the compilation again. Another disadvantage is that this is is machine dependent. If you want to import or transport your machine code to a different machine, then you're probably going to have to recompile it. So it has its advantages and disadvantages. In contrast to this, Julia does it a third way. So this is also called as dynamic compiler. So the Julia script is run through a just-in-time compiler as it is running. And so it's generating machine code on the fly as it runs. And it uses the original script itself to make optimizations on the fly. This means that it has the best of both worlds, at least in theory. It's an interpreted language, and it's interpreted from your perspective, but it's also compiled when you run it. This is why it's called just-in-time compiler, just in time for execution. There is a somewhat there's an issue here that I will not cover in depth, but there's an overhead that you have to face when you use Julia, which is it does take a little bit of time to start running your code because it uses a just-in-time compiler. But as I said before, as your Julia scripts become more and more complex and needs more and more computational power, then it becomes more and more worth it to go through this initial slowdown. And next, I want to just give you a brief list of the scientific packages that are available in Julia, and there are many more than this, but this is just to show you that if you want to use Julia in a research project, if there are packages available to do that. There are packages for differential equations, packages for optimization, visualization. There's a few. Again, some people are not satisfied with the packages that Julia has, but you can use Python as a backend, and that works well as well. If you're doing machine learning, since the initial days of Julia, machine learning was one of the goals that the developers had in mind, to have a language that was good for machine learning and deep learning. So we have Flux and KNet and a few others. And as I said before, our example will show you how to use Flux, right, and how to install the Flux package. And then if you want to use Jupyter with Julia, all you have to do is install the iJulia package, and then you should be able to access the Julia kernel from Jupyter. So to summarize the pros of using Julia, from my perspective, is the easy syntax. It's very easy to code in, and also it's very easy to review other people's code. This is a great advantage. It's compiled, and this is in principle faster than interpreted languages. So especially if you're thinking planning on running fast, large scale simulations or large scale analysis, this could be a big advantage for you. It's dynamically typed. This is a desirable feature, as I mentioned before. You don't have to declare types in Julia, although you can predefine types in Julia as well, if you need to. It is interoperable with other languages from the beginnings of Julia. This was one of the features that was in the developers' mind to make Julia interoperable with other languages. As I said before, you can make calls to Python, you can make calls to R, even Matlab and C and others. But I have to show you the cons of using Julia too. I have to, at least from my perspective. The number of mature packages is small, and after using and looking for packages for a Julia project, you will realize that some of them are not maintained very well or are not maintained very often. Others make big changes to the package itself, and this is not something you would do in a in Python, for example, with the packages are usually mature, they're stable, and they're well maintained in most cases. Something to also keep in mind when you are developing in Julia, or if you're planning to develop in Julia, is that there is still a relatively small scientific community for it. So if you start using Julia on a research project, you are unlikely to find other colleagues that are using Julia. So you will see that, although that is changing rapidly. There's relatively limited support, and this has also changed in the past year or two. It's becomes easier and easier to find answers to technical questions that you might have when facing a complicated issue in Julia. So with regards to the Julia integrated development environments, or IDEs, there's a number of them. There's the very simple ones, but I wanted to show you just three to give you a list of three. You can use VS Code. VS Code, as I mentioned before, it can run on your desktop computer, and you can edit, debug, and execute and version your scripts remotely. And this is important if you are working remotely, like you do, like Biowulf users do. We also, for interactive computing or interactive coding, you can use Jupyter, and this works also very well, although this is only for interactive computing. And then there's Juno, which is the most popular IDE in Julia at the moment, although the last Julia conference, I read that at the last Julia conference, that Juno was probably going to go into maintenance only mode. And this is because the development of Juno is going to be focused now on improving the Julia extension for VS Code. And so if you are running VS Code, I know many of you use it for Python and some for R. We have details on how to use VS Code on the compute nodes on Biowulf. Just go to the address on the link, hpc.nih.gov/apps/vscode.html. The link is on the screen. The only thing I would like to ask you is, if you run VS Code on Biowulf, not to run it on the login node, not to run it on Biowulf itself or Helix. If you're going to run it, the proper way to connect is to the compute node directly. And this is because when you run VS Code, even if it runs in the software, VS Code is installed locally in your desktop computer, VS Code spins up a server on the other side. So this is computational intensive, and on Biowulf, if you are connected remotely to Biowulf. So we ask you to please check out the steps on the website on how to connect to compute nodes directly. And yes.
So there were a couple of questions in the chat I think might be interesting in general, and they back up slightly to what you talked about previously. Question number one, can you sort of reiterate a difference between interpreted versus just-in-time compilation? And the second question is, are there any specific fields where Julia is more popular than others? What does it look like in bioinformatics and computational biology, for example?
Yes. So for the first question, an interpreter language is, an interpreter is when you start with your original script, and then the interpreter is going to go to process that script line by line and executing it line by line. So you get an almost instant execution to start execution. But because it's doing it line by line, there's no optimization based on what happens in the rest of the script. And so this is not an issue for simple scripts, but as your script gets more and more complex, there are many optimizations that can be done to speed up execution. So that doesn't happen in an interpreted language in simplistic terms. So now a compiler, in contrast, processes the original script, and it looks at the whole thing. It has visibility over all of the whole script, and it generates a machine code that corresponds to that script. And that machine code is very, very fast. You can run it as many times. You can have as many copies of the machine code as you want, but that machine code is specific to that machine in which you compiled it. So it cannot be imported to other machines, to other types of machines. So those are two types, interpreted and compiled. Now, Julia uses a third way, which is the just-in-time compilation. So the just-in-time compilation is also known as dynamic compilation because it compiles the script on the fly. So it looks at the original script, and it starts execution, and at the same time compiles the script as it's executing it, and tries to infer types. For example, at the first use of a function, just to mention an example, that function is compiled, and the types are inferred from the specific function that was found. And so when that function is used again in the code, in the same script, then the same compiled function is used. So that means that it speeds up the function. It doesn't have to compile it again, unless the function has a different type, then it's recompiled, and there's nothing written to disk. It's just going on the cache, and so it does it on the fly. And so this is just what Julia uses, or what is called as just-in-time compilation. Right? And the second question, sorry, what was the second question?
Are there any scientific fields where Julia is more popular than others? What does it look like in bioinformatics and computational biology?
Yes, the graphs that I have seen are showing Julia doing really well in the field of data science, not yet in scientific computing itself, much less in bioinformatics. So I don't think Julia has really started picking up in the bioinformatics field yet. At least that's the way, that as far as I know, that's the current status of Julia. Okay, so let me now move to the example. So yes, so just to add to my previous answer to the question, so it is something to consider that Julia is not still very often used in bioinformatics in general, because then you will not have colleagues that you can share your code with, or that you can collaborate with if you are doing things mostly in Julia, although that might change in the future. But I see Julia being in the place that Python was back in 2009, 2010, when it was starting to pick up. It was starting to be used more and more. So it's looking better and better for Julia usage. So even if you don't use it as your main language, it'll be good to check it out and know how to use it. Things might change in the future. Yes. But let me go to the example. So I'm going to present a demo of a machine learning example using the Flux package. And we are not going to write the script. The script, we're going to download it, or we're going to clone it from the GitHub repository of the Flux package developers. So if you haven't used Git, this is something very useful to have in your workflow. It's very common to use Git for not just for versioning your own code, but also for cloning code, even if you're not going to contribute to someone's code. So, and let me let me explain that what the example is going to do very shortly. It's a very simple example. So we're going to have a problem. It's a very classic. It's a classic problem in machine learning. Of it's the recognition of handwritten digits. So this basically consists in a number being used as an input to a blue box that we see on the screen. This blue box is a script that has to look at that image of the number and categorize it as the correct number. In this case, you see on the left there's a handwritten 9, or what looks like a 9, and so this should correspond to the actual number 9, or to the category 9. As you can imagine, the number 9 can be handwritten in an infinite number of ways. So this is a complicated issue, but it's one that has been around for a while as a benchmark for machine learning methods to deal with. So, and we have numbers from, in this example, from 0 to 9 is just the digits, and the output should go to one of the categories between 0 and 9. And that blue box in this example is going to be a neural network script. It will be what is called a multi-layer perceptron script, and we're going to obtain it from the GitHub repository of Flux. So the input is the blue spheres on the left indicate just the number of pixels in the image. There are many more pixels than that. That's just a cartoon, and the output has to be one of the categories. Which category does the input belong to? And so we have n number of pixels and 10 possible categories for that number. And we have in the middle, simplistically speaking, neural network with a number of weights, and the weight, the training, so-called what we call the training in neural networks, has to adjust the weights so that the network is able to categorize the numbers after training. And so we use, in this example, we're going to use a set of 60,000 images from the database called NIST, MNIST, or modified NIST. There is a Julia package where you can download that you can import so that you can have access to data sets. And this is one of those data sets. So we're going to install that package with the data sets, and we are going to import the library. So the script has to process for training 60,000 images, and then at the end be able to recognize digits above a certain threshold. And so this is what happened. And as I mentioned before, a handwritten input, the picture of a handwritten input is shown to the script, and then the script just spits out an answer. But it's only the training that we're going to do. The script only does the training. So that's the training on a set of inputs, that items in the database I use for training, and then it tests on a testing data set. And the output of this is just a printout of what the success rate looks like at different stages in the processing. And so these are the steps that we're going to use for the example today. As I said at the beginning, if you can either follow the example as I do it and do it later with the slides if you download them from the HPC website, or you can do it as I do it. It's a very simple example. You might have issues if you are trying to request a GPU. I myself requested a GPU prior to the class, so I already have allocated a GPU for the example. But if you find that you're waiting a long time for the GPU, know that you can also use CPU. The script will run a little bit slower, but you will get your allocation faster. So the first step is going to be connect to Biowulf. For this example, we're not doing any graphics. Everything is text-based. So any application will do. You can use PuTTY or PowerShell if you're on Windows. You can use the Mac term or the Linux term in those platforms, or you can use No Machine if that's what you use it, or any other platform that lets you connect to Biowulf. Then we're going to start an interactive session. So in this example, I requested memory of 10 gigabytes. This is more than enough for our example today. And if you like, you can already start doing this in your screen. If you are able to connect to Biowulf and start doing this now, because it can take some time to wait for the resources to be allocated to you. But continuing with the S-interactive command, we see there -C14 that indicates that I am requesting 14 CPUs for this task, which again is more than enough for our purpose today. And then we have --gress, again on the red box. And those are just extra resources equals to lscratch :2. That just indicates that I am requesting a local disk allocation of 2 gigabytes, which is enough more than enough for our script and for our execution. And then we have comma GPU for this S-interactive session. I'm requesting a GPU. We have different types of GPU. In this case, I'm requesting a P100, and I'm requesting one of them to have with my allocations. So after I do this, I already have allocated my resources for my script to run. Let me go to my screen here, because I am already on the second step. And so you see my screen on the left. This is already gone through the first and second steps, already logged into Biowulf, already started an interactive session with those resources on the right side of the screen. And now I am going to load the Julia module. As I mentioned before, applications are organized by modules on Biowulf. So every time you want to run an application, you have to load the corresponding module for that application. So I'm going to type module load Julia, and this is going to set up anything that is needed for me to run Julia. And so this is step number 3. And so we go to step number 4. Step number 4, we're going to move into the disk space that we allocated for this interactive session. In this case, it's learn job ID. Then we're going to run Julia, and just gives us the interactive session. Sorry, excuse me, the interactive shell for Julia. Here we click the right square bracket, and we enter the package manager, and we install the packages that we need to install. In my case, I already pre-installed these packages. For me, it's going to be a little bit faster. I pre-installed these packages before the class. So at some point, this will go through, but it won't take as long as if I was installing the packages from scratch. So we can check the status of packages with the command status just to see what packages we have installed. And then we exit Julia. This is Control D, exits the package manager and Julia. And then we're going to clone the repository. And this should not take very long either. And then we are going to run it after. So we're going to move in the step 10, we move into the directory. And then this is optional, step 11, just using Nano, which is a bare bones editor for your scripts. So to look at text scripts. Then step 12 is exit Nano, and then you run your machine learning example. So while this runs, I wanted to get some input from you. I have a survey so that you can show it before we're almost out of time. So you can wanted to get some input from you on future classes, just for future offerings. If you have any interest, please enter your interest in there, and we will consider that. So now, while the poll is going on, I'm going to go to the rest of the steps. Saved. I'm gonna use I'm gonna clone the repository. This is super fast. Then I look at what's in there. I enter the directory, model zoo, vision, and there are more examples in this same repository if you like to look at them. And then we just run our code. Okay. So if you, so the code, what's going to happen with the code is going to write out a results at each stage, which are just the what corresponds to the error and the performance, the accuracy at each step. And at some point, it'll end up with 90% plus accuracy. So, but anyway, we can continue. You can continue this offline. I don't want to take more time than it was allocated than you allocated for the class today. So it's already 11 o'clock. I'm going to polling. So just in conclusion, excuse me, in conclusion, so hopefully now you have a general idea of the pros and cons of using Julia, and also are generally familiar how to run Julia scripts interactively on Biowulf. If you have any more questions, you can send them to staff at the email address on the screen. And if you run into any errors that you cannot solve, please get in touch, and we will try to help you out. Thank you.